In 1981, astronomers mapping the universe discovered a vast region nearly 300 million light-years in diameter that was almost completely empty of bright galaxies and star-filled clusters. This feature, known as the Boötes Void, has since been a significant cosmic mystery regarding its origin and its implications for our understanding of space. The common perception of the universe is of a dense and active space, filled with swirling galaxies, stars, and colorful clouds of gas and dust. Our own Milky Way galaxy appears full of stars and planets, and beyond it are countless other galaxies of various shapes, all illuminating the darkness. The night sky offers a small sample of this view, hinting at a vast and dynamic cosmos characterized by events like star formation and galactic collisions. The universe contains a number of stars and galaxies that is beyond enumeration. However, this image is incomplete, as a substantial portion of the universe is nearly empty. The bright galaxies and stars are dispersed throughout immense regions of emptiness. These large, quiet areas, known as cosmic voids, are massive bubbles in the universe where galaxies are scarce or entirely absent. Light takes millions or even billions of years to traverse them, and their matter density is extremely low. Within these voids, there is a profound absence of light heat and significant gravitational influence. To visualize the universe's structure, it is useful to use the analogy of a sponge, where galaxies and clusters form the dense material, and the voids are the hollow parts that constitute a large fraction of cosmic volume. These voids are substantially emptier than the space between planets in our solar system. Placing the Milky Way inside one would be comparable to a single grain of sand in a large stadium with its nearest neighbor potentially billions of light-years away. While not entirely devoid of matter, cosmic voids contain sparse atoms such as hydrogen particles and the faint radiation of the cosmic microwave background from the Big Bang. Their emptiness surpasses that of man-made vacuum chambers on Earth. This contrasts with galaxy clusters, where hundreds or thousands of galaxies can be situated closely together, connected by filaments. The few galaxies that exist inside voids are typically faint, isolated, and drifting alone. Consequently, light in these regions is extremely scarce. The existence of these large, empty spaces is an integral feature of the universe's structure. They originated from small variations in the density of matter and energy in the early universe. Over billions of years, gravity amplified these differences, pulling matter into denser regions that would become stars, galaxies, and clusters. The less dense areas were consequently stretched and emptied as matter migrated away from them. The expansion of the universe further enlarged these voids, sculpting the cosmos into its current sponge-like structure of bright clusters and filaments surrounding vast, quiet voids. Therefore, the empty space between celestial objects is as fundamental to the universe's structure as the stars and galaxies themselves. These silent voids, though not luminous, are a critical component of the cosmic architecture. The scientific interest in these regions is focused on what their emptiness reveals about the invisible forces, gravity, dark matter, and dark energy that shape the universe. These forces explain why the cosmos is not uniformly filled, but is instead organized into giant clusters of matter and nearly deserted voids. Voids are regions of physical quietude, with no new star formation, galactic interactions, or energetic black holes. The isolated galaxies that reside within them are not gravitationally disturbed by neighbors, causing them to have quieter, slower lives. This lack of interaction may lead to different evolutionary paths, such as retaining their gas for longer periods or forming fewer stars. Cosmic voids represent an extreme version of a vacuum, existing as enormous natural gaps in the fabric of the cosmos that can be hundreds of millions of light-years wide. As some of the emptiest places in existence, they challenge conventional ideas about nothingness and the distribution of matter in the universe. If an observer were in the center of a giant void, the sky would appear almost completely black, with only faint distant stars or galaxies barely visible. The light from the closest bright object would have traveled for hundreds of millions of years, offering a view of the cosmic past. This visual emptiness contributes to what is known as cosmic silence. This silence is also gravitational. Due to the immense distances to massive objects, their gravitational pull within a void is negligible. The matter that exists there is left largely undisturbed, and these regions expand faster than the rest of the universe due to dark energy. The temperature in these voids is only a few degrees above absolute zero, warmed solely by the cosmic microwave background. They are places of extreme cold darkness and stillness. Despite their apparent emptiness, cosmic voids are highly valuable to scientists because they contain very little ordinary matter. The gravitational interference that is present in crowded regions of space is absent. This makes voids ideal environments for studying the effects of dark energy more clearly. In these expansive, quiet voids, there is little to obstruct or distort the effects of dark energy, making them ideal environments for studying how this force may be driving the universe's expansion. By analyzing the size, shape, and growth of voids over time, scientists aim to find new insights into one of physics's greatest mysteries. Although they appear empty, these voids are significant. Their vast stillness directs us toward fundamental truths about the universe, its formation, its evolution, and the invisible forces that govern it. These cosmic gaps are not merely empty spaces, but windows into the universe's underlying structure, containing silent histories and subtle clues. For millennia, humanity observed the night sky with unaided eyes, perceiving only points of light against the darkness. This limited early cosmological understanding to what was directly visible. The invention of the first telescopes initiated a profound change, revealing new worlds and fainter stars. In time, it was discovered that our Milky Way was just one of many galaxies, and the perceived scale of the universe expanded. By the mid-20th century, astronomers had grasped the universe's immense size and held a model in which galaxies were distributed more or less uniformly throughout space. This concept was logical and widely accepted until an unexpected discovery entirely altered that view. It demonstrated that galaxies were not evenly spread, but were largely absent from enormous regions of space. This finding marked a new era in understanding cosmic structure, and central to this revelation was the identification of the Boötes Void. This discovery was made in the early 1980s by a team of astronomers led by Robert Kirshner, which included Augustus Oehmler Jr., Paul Schechter, and Stephen Schechtman. They were engaged in a large-scale project to map the distribution of galaxies. Their work required more than just locating galaxies in the sky. To create a true map of the universe, they needed to determine their distances from Earth. This third dimension was essential for building a three-dimensional model, illustrating how galaxies form clusters and filaments, leaving vast empty areas between them. To achieve this, they utilized a technique known as redshift. Redshift is analogous to the change in pitch of a receding siren, where sound waves are stretched. Similarly, as a galaxy moves away from us, its light waves are stretched, shifting them toward the red end of the spectrum. The greater the redshift, the faster the galaxy is receding, and the more distant it is. This principle is based on the work of astronomer Edwin Hubble in the early 20th century, who found that nearly all galaxies are moving away from us and that more distant galaxies recede faster. This relationship, known as Hubble's law, enabled scientists to calculate a galaxy's distance by measuring its redshift using redshift. Kirshner's team observed thousands of galaxies in a specific region of the sky. They collected faint light from these distant objects and separated it into a spectrum to analyze its patterns. These spectral patterns revealed each galaxy's elemental composition and, crucially, the degree to which its light had been stretched. From this data, they calculated the distance to each galaxy. As they compiled their observations, a detailed three-dimensional map of galaxy locations began to emerge. During this process, they noticed a peculiar anomaly in the direction of the constellation Boötes, an immense volume of space with a near-total absence of galaxies. This was not the result of instrument malfunction or obscuring dust. Their equipment was functioning correctly, and they could observe galaxies both closer and farther than the empty region. What they had found was a vast spherical area, hundreds of millions of light-years in diameter, that was almost entirely devoid of matter. In 1987, after extensive study, the team formally announced their discovery in a scientific paper, naming the region the Boötes Void. The Boötes Void was one of the largest cosmic structures ever identified, with initial estimates placing its diameter at approximately 250 million light-years. For perspective, the Milky Way galaxy is only about 100,000 light-years across, meaning thousands of galaxies like our own could fit inside the void. Yet it contains only a small number of them. This discovery was a turning point, proving that the universe is not a uniform scattering of galaxies. Instead, it possesses a definite structure of dense clusters and long filaments of galaxies that enclose vast empty regions. This finding led to a new conception of the cosmos as a cosmic web, with galaxies situated along interconnected threads that surround enormous voids. The Boötes Void, as one of the most prominent features of this web, was instrumental in revealing the hidden architecture of the universe and the pattern distribution of matter. The scientific community reacted to the discovery of the Boötes Void with astonishment and excitement. The void's sheer size and what it implied about the universe's structure challenged existing models which had largely assumed a relatively even distribution of matter. A region of such scale and emptiness did not conform to the prevailing picture of a balanced cosmos. This unexpected finding stimulated a new wave of research focused on the early universe to understand how such an enormous void could have formed. It also intensified inquiries into the roles of dark matter and dark energy, the unseen components believed to shape the universe's structure and destiny in creating both dense galactic clusters and empty regions like the Boötes Void. Furthermore, the discovery underscored the importance of large-scale redshift surveys. Previously, astronomers had often concentrated on individual or small groups of galaxies. The Boötes Void made it evident that comprehending the universe's structure required mapping much larger volumes of space, prompting a shift in perspective. The universe came to be seen not as a simple collection of galaxies, but as a vast interconnected system, characterized by areas of both high density and near-total emptiness. In the years that followed, improved instruments and more advanced redshift surveys confirmed the existence of the Boötes Void and identified other similar voids. Researchers also discovered a few isolated galaxies within the Boötes Void itself. The isolation of these galaxies makes them scientifically valuable, as they provide a unique opportunity to study galactic evolution in an environment free from the strong gravitational influences typical of more crowded cosmic regions. The techniques and tools developed to study the Boötes Void have since become standard in the ongoing effort to map the universe, leading to the discovery of countless other structures. The Boötes Void evolved from being a curious anomaly to a symbol of scientific progress, a reminder of the universe's capacity for surprise. Its discovery revealed a hidden aspect of the cosmic design, one far more complex than previously imagined. It showed that the universe is shaped by both concentrations of matter and immense silent voids, and that sometimes the most profound truths are found in the emptiest of places. The universe's vastness renders conventional units of distance, such as kilometers or miles, impractical. For cosmic scales, the light year is the standard measure representing the distance light travels in one Earth year. Light moves at approximately 300,000 kilometers per second, making a light year equivalent to about 946 trillion kilometers. The immense distances in the universe mean that even light requires significant time to travel between celestial objects, and the scales involved are difficult to comprehend from a human perspective. One of the largest known features in the universe is the Boötes Void, a vast, empty region of space. Astronomers estimate its width to be about 250 million light-years, meaning light would take 250 million years to travel from one side to the other. This duration is more than 5% of Earth's age, which is approximately 5 billion years. The void is not a flat area, but a three-dimensional, nearly spherical volume of space. To contextualize the void's immensity, it can be compared to the Milky Way galaxy. The Milky Way, which contains 100 to 400 billion stars, is about 100,000 light-years in diameter. It would take 2,500 Milky Way galaxies placed end to end to span the diameter of the Boötes Void. If the Milky Way were positioned in the center of the void, it would be an isolated speck in a vast emptiness. From a location within the void, the night sky would appear profoundly empty. The nearest galaxies could be hundreds of millions of light-years away, potentially appearing as faint smudges, if visible at all, through powerful telescopes. Such a region would lack the gravitational interactions and nearby supernovae common in denser parts of the universe. The spaces between galaxies are so large that the concept of galactic neighborhoods is not applicable. The Milky Way is part of the Local Group, a cluster of galaxies that also includes the Andromeda and Triangulum galaxies, along with about 50 dwarf galaxies. The Local Group spans approximately 10 million light-years. About 25 local groups would be needed to extend across the diameter of the Boötes Void. This comparison demonstrates that the void is empty, not just relative to single galaxies, but also to entire galaxy clusters where gravitational interactions are common. The Boötes Void can also be compared to galaxy clusters, which are gravitationally bound. Collections of hundreds or thousands of galaxies, typically measuring from 3 million to 30 million light-years across the Virgo cluster, for example, is about 10 million light-years wide. Numerous such clusters could be aligned side by side within the void's expanse. The density of a galaxy cluster contrasts sharply with the emptiness of the void. Larger still are superclusters, which are massive structures of galaxy clusters and groups connected by gravity. Stretching for hundreds of millions of light-years, the Laniakea supercluster, which includes the Milky Way, is about 500 million light-years across. The Boötes Void, with its 250 million light-year diameter, is larger than many superclusters and is comparable in scale to the largest known structures in the universe. The universe's large-scale structure resembles a sponge with galaxy-rich filaments and walls separated by enormous voids. The Boötes Void is one of the largest of these empty spherical bubbles. Its radius is about 125 million light-years. In terms of volume, the void is billions of times larger than the Milky Way galaxy. This vast volume is defined by the significant absence of galaxies. Traveling across this expanse would be a journey of immense duration. A hypothetical spaceship moving at 1/10 the speed of light would take over 25 billion years to cross the Boötes Void, a period comparable to the 35 billion year history of life on Earth-current spacecraft, such as the Voyager probes, travel at speeds that would require a transit time far exceeding the current 13.8 billion year age of the universe. Traveling such a vast distance is incomprehensible. Communication across this expanse would also be exceedingly difficult. Even light, the fastest known entity, requires hundreds of millions of years to traverse the void. A signal sent from within the Boötes Void to another galaxy would take longer to arrive than the entire history of human civilization. If life could exist within the Boötes Void, its inhabitants would experience profound isolation. The closest galaxies would lie tens of millions of light-years distant, and the only visible celestial objects might be the dim, ancient light from galaxies so remote their light has traveled for hundreds of millions of years. This level of solitude is difficult to imagine. When scientists describe the Boötes Void as a void or empty space, they do not mean it is a true vacuum. In cosmological terms, empty signifies a region with significantly less matter than other areas of the universe. Even the most desolate sections of the Boötes Void contain drifting hydrogen atoms, occasional photons from the cosmic microwave background, and dark matter, which is detectable though not visible. However, compared to the universe's average matter density of a few atoms per cubic meter, the Boötes Void may contain less than 1 atom per cubic meter and possibly far fewer. This characteristic makes it one of the most underdense regions known. Despite its emptiness, astronomers have identified approximately 60 isolated galaxies within the Boötes Void. These galaxies are extremely isolated, separated by distances of tens of millions of light-years. While such a distance would be immense elsewhere in the universe, it is typical within the Boötes Void. This significant emptiness is more than a curiosity. It reveals profound insights into the structure of the universe. The universe is not smooth or evenly filled with galaxies. Instead, it is clumpy and uneven, comprising bright, dense regions of light as well as vast, quiet expanses of darkness. The Boötes Void exemplifies one of these silent regions. Studying it compels a revision of our understanding of the universe. It shows that the cosmos consists not only of brilliant stars and galaxies, but also of profound silence and immense emptiness. Locating the Boötes Void within the universe requires an understanding of cosmic geography, which is the large-scale arrangement of the cosmos. Similar to Earth's structure of continents and oceans, the universe possesses an architecture on a vastly larger scale. Stars and galaxies are not randomly scattered. They form an enormous interconnected pattern known as the cosmic web. The cosmic web consists of immense, delicate strands called filaments, which are dense with galaxies and extend for hundreds of millions of light-years. The intersections of these filaments form massive nodes, where galaxies are concentrated in dense clusters. Between these filaments and nodes are vast empty regions known as cosmic voids, which are large areas containing very few galaxies, stars, or matter. The Boötes Void is one of the largest and most prominent of these voids, existing as a massive, nearly empty bubble within the cosmic web. To understand its location, one must first understand our own position. Our cosmic location begins on Earth, one of 8 planets orbiting the Sun, a middle-aged star. The Sun is one of hundreds of billions of stars constituting the Milky Way galaxy. The Milky Way is a spiral galaxy of stars, dust and gas, spanning approximately 100,000 light-years. The Sun resides within one of the galaxy's spiral arms, about 27,000 light-years from the galactic center. The Milky Way is also part of a small collection of galaxies called the Local Group. The Local Group, which spans about 10 million light-years, includes the Milky Way, the Andromeda Galaxy, and approximately 50 smaller dwarf galaxies. The Local Group is gradually being drawn towards the much larger Virgo cluster, located about 55 million light-years away. Both the Local Group and the Virgo cluster are components of an even larger region known as the Laniakea supercluster. The Laniakea supercluster is an immense gravitationally bound area of the universe extending roughly 500 million light-years and containing numerous galaxies, clusters, and filaments. Therefore, our complete cosmic address is Earth Solar System, Milky Way, Local Group Virgo cluster, and Laniakea supercluster. With an understanding of our own position in the universe, we can then locate the Boötes Void. From Earth, it is located in the direction of the constellation. Boötes, also known as the herdsman constellations, are apparent groupings of stars in the night sky, though their constituent stars may be widely separated in 3-dimensional space. Therefore, stating that the Boötes Void is in the direction of Boötes means that observing this region of the sky and measuring galactic distances reveals a vast, spherical, 3-dimensional area that is nearly devoid of matter. It is not merely a dark patch in the sky, but a massive bubble-shaped void in the universal structure. The center of the Boötes Void is estimated to be approximately 700 million light-years from Earth. This means that light from its center started its journey to us 700 million years ago, when complex life on Earth was just beginning to emerge in the oceans. Consequently, observing the Boötes Void is an act of looking deep into both space and time. This immense silent region is one of the most mysterious and compelling features of the universe's design. The Boötes Void is not located just outside our galaxy. It resides at an immense distance, far beyond our local galactic neighborhood and even beyond the Laniakea supercluster. Reaching the nearest edge of the Boötes Void would require a journey of several hundred million light-years. This classifies it as an exceptionally remote feature in the cosmic landscape. On a large-scale map of the universe, with Earth at the center, the Boötes Void would be a vast, dark, empty bubble situated far from us, beyond both the Milky Way and our entire supercluster. It is a feature of the distant universe, not a local or nearby phenomenon. The Boötes Void is a prime example of a cosmic void. These are vast, empty regions that contribute to the large-scale structure of the universe. This structure can be visualized as a giant sponge or a network of soap bubbles where the luminous parts of the universe, such as galaxy clusters and superclusters, are concentrated on the surfaces of these bubbles. These luminous threads and walls, known as filaments, are where matter has aggregated over billions of years due to gravity. The hollow interiors of this structure are the voids, which are extensive regions of space containing very few galaxies. The Boötes Void is one of the largest and most distinct of these empty regions. If filaments are analogized to busy cosmic highways teeming with galaxies, then the Boötes Void is like a massive deserted plaza within this system. It is a seemingly inactive region that nonetheless plays a crucial role in the universe's overall architecture. The existence of the Boötes Void demonstrates that matter in the universe is not distributed uniformly, but is organized in a complex, foam-like pattern. Surrounding the Boötes Void, astronomers have observed some of the largest structures in the universe. The void, though nearly empty, is enclosed by denser regions of the cosmic web similar to a hollow space within a sponge. For example, portions of the Hercules and Corona Borealis superclusters are situated nearby, although they are still hundreds of millions of light-years distant. These large collections of galaxies define the edges of the void. The Boötes Void is an immense expanse of emptiness that separates these large superclusters of galaxies. Over billions of years, the gravity from surrounding cosmic structures has drawn matter towards them, leaving the Boötes Void increasingly empty. This process is amplified by the expansion of the universe, which causes the void to stretch and grow larger. Consequently, the Boötes Void is a fundamental component of cosmic organization, signifying the expansive open spaces between dense galactic regions. An analogy can be drawn to a world map, where continents represent the high concentration of galaxies and stars, and the vast, largely empty oceans correspond to cosmic voids. In this comparison, the Boötes Void is akin to one of the largest oceans, an immense expanse of emptiness situated between the continental masses of galaxy clusters. Much like a vessel in the central Pacific would see no land, a galaxy traversing the center of the Boötes Void would be isolated in an immense dark expanse. This analogy illustrates that the Boötes Void is not a coincidental empty area, but a significant element in the universe's structure. While numerous other cosmic voids, varying in size from approximately 10 million to several hundred million light-years, have been identified, the Boötes Void continues to be one of the most notable. As one of the first truly massive voids discovered, its immense scale was astonishing to astronomers upon its detection. Consequently, it has become a standard example or model void for understanding similar structures. Although not unique, it is distinguished by its clarity and its stark demonstration of the potential emptiness of certain cosmic regions. Its position within the cosmic web, encircled by luminous galactic filaments and clusters that constitute the universe's framework, is characteristic of large voids. Examining how the Boötes Void integrates into this large-scale pattern allows astronomers to validate theories of cosmic evolution. For instance, observing the arrangement of galaxies at the void's periphery and its growth over time provides insights into the enigmatic force known as dark energy. This unseen energy is thought to stretch space itself, contributing to the expansion of these empty areas. Therefore, the Boötes Void is a significant feature of the cosmic landscape, not merely an empty space. Its location, form, and connection to the surrounding galactic filaments offer astronomers crucial clues about the invisible forces that shape the universe. It serves as a silent yet potent testament to the dynamic processes that have shaped the universe into a structure of matter and void over billions of years. Gravity is frequently described as the weakest of nature's four fundamental forces. This might seem counterintuitive, given its apparent control over everything from falling objects to planetary orbits. However, despite its weakness, relative to forces such as electromagnetism and the strong nuclear force, gravity has methodically formed the most massive and grand structures in the universe. Over billions of years, gravity has operated slowly and persistently to draw matter together. It has converted diffuse gas clouds into luminous stars, gathered those stars into rotating galaxies, and assembled those galaxies into larger formations like clusters, superclusters, and the elongated thread-like filaments of the cosmos. This complex arrangement, known to astronomers as the cosmic web, extends throughout the universe. Yet gravity's role is not limited to construction. It also clears out regions. Gravity is also the force behind the formation of immense empty expanses of space called cosmic voids, which are vast dark areas with a scarcity of galaxies. The Boötes Void is a prominent example of such a large and empty cosmic region. Therefore, gravity not only aggregates matter into dense cosmic concentrations, but also creates the vast empty spaces between them, acting as a cosmic sculptor that shapes the universe through both accumulation and depletion. Fundamentally, gravity is an attractive force between any two objects possessing mass or energy. The strength of this attraction increases with the mass of the objects and their proximity to one another. Isaac Newton first articulated this principle in the late 17th century, and it was later refined by Albert Einstein's theory of general relativity in the early 20th century. This fundamental force is responsible for phenomena as simple as a falling apple and as complex as the rotation and movement of galaxies across vast cosmic distances following the Big Bang. Approximately 13.8 billion years ago, the universe was characterized by extreme heat density and near-perfect uniformity. The crucial deviation from perfect smoothness was the presence of minor density fluctuations. In regions with slightly more matter, gravity was marginally stronger, initiating a slow accumulation of additional matter. As material gathered, the gravitational pull intensified, attracting even more matter in a process known as gravitational instability. These initially small, denser regions evolved into the foundational structures of the universe, eventually forming galaxies, clusters, and the extensive filaments of the cosmic web over billions of years. Conversely, in the initial low-density areas, gravity was weaker. As denser regions attracted matter, they effectively drew it away from these less dense neighboring areas. Unable to retain their sparse material, these regions were gradually depleted, becoming progressively emptier. In this manner, gravity's role in congregating matter in some locations concurrently emptied others, leading to the formation of vast cosmic voids, such as the Boötes Void, which resulted from matter being drawn away by more massive surroundings. A comprehensive understanding of this process requires considering dark matter, a substance that does not emit, reflect, or absorb light, making it invisible to direct observation. Its existence is inferred from its gravitational effects on visible matter. Dark matter constitutes approximately 85% of all matter in the universe, with visible matter such as stars, planets, and gas accounting for the remaining 15%. Despite being invisible, its gravitational influence is significant. In the early universe, the initial density fluctuations were primarily variations in dark matter. These concentrations of invisible matter formed powerful gravitational wells that attracted both dark and ordinary matter. Regular gas and dust were drawn into these wells, where they cooled and eventually formed stars and galaxies. In the absence of these dark matter concentrations, ordinary matter would not have aggregated sufficiently to create significant structures, leaving the universe largely uniform and devoid of galaxies, stars, or life. The cosmic web, the large-scale pattern of filaments, clusters, and voids, is fundamentally a dark matter framework. The filaments serve as conduits of dark matter, guiding galaxies along their paths, while clusters are massive concentrations of dark matter functioning as galactic centers. Voids such as the Boötes Void are regions with a low density of dark matter. The visible galaxies are merely luminous markers situated upon this larger invisible dark matter scaffold. The emptiness of the Boötes Void is likely attributable to its initial low concentration of dark matter. Lacking sufficient gravity to attract and retain matter, it progressively lost its material to adjacent denser areas over billions of years, evolving into a vast, isolated region of the cosmos. These same principles of gravity operate on smaller scales. Within large gas clouds, gravity draws atoms together to form stars, which in turn attract each other to create star clusters. At a larger scale, gravity consolidates billions of stars, gas and dust into galaxies such as the Milky Way. Our galaxy's spiral structure is itself a product of gravity, with the entire system bound by a surrounding halo of dark matter. On even grander scales, gravity's influence persists. It attracts not only stars and planets, but also entire galaxies, such as the Milky Way and Andromeda, causing them to move toward each other. Over cosmic timescales, these galaxies assemble into small collections like our own local group. This process continues as galaxy groups are gravitationally drawn towards still larger concentrations of matter, coalescing to form galaxy clusters that may contain hundreds or thousands of galaxies. The powerful gravity of these clusters attracts nearby galaxies, drawing them toward the dense core. Furthermore, these massive clusters are frequently interconnected by long, slender filaments composed of galaxies which extend across space. Galaxies travel along these filaments, following gravitational pathways toward the most massive clusters. This immense interconnected structure of clusters and filaments constitutes what is known as the cosmic web. A vast web-like structure extends across the universe, where gravity has effectively gathered matter into dense connected formations, slowing the natural expansion of space in these locations. Not all of space, however, is occupied by galaxies and clusters. There are also voids, which are giant dark and nearly empty regions of the universe. Voids are the opposite of filaments. As gravity draws matter into the cosmic web, it leaves behind immense stretches of emptiness. One of the most notable of these empty regions is the Boötes Void. The Boötes Void is exceptionally large and sparse. It originated as a region of slightly lower density in the early universe, containing less dark matter than adjacent areas. Over billions of years, gravity from the surrounding filaments and clusters pulled matter away from this underdense region, further emptying the Boötes Void. Within this vast emptiness, only a few galaxies, often called lonely galaxies, remain. These galaxies either formed from residual patches of matter within the void, or were too isolated and small to be extracted by the gravitational pull of nearby structures. Their isolated existence demonstrates the power of gravity, which effectively cleared the surrounding space, leaving them stranded. Gravity operates very slowly, and its effects are not immediate. It takes a considerable amount of time to shape the universe, which has been evolving for approximately 13.8 billion years since the Big Bang. In its early stages, the universe was not perfectly uniform, with some areas having slightly more matter than others. These minor initial density differences were sufficient for gravity to act. Over billions of years, gravity pulled on the denser areas, causing them to grow into the galaxies, clusters, and filaments observed today. Simultaneously, the less dense regions, the voids, became even more empty. Although gravity is the weakest of the four fundamental forces, its slow and steady influence has reshaped the cosmos. It transformed minor fluctuations in the early universe into enormous structures that maintain their cohesion even as space expands. In this process, gravity constructed the luminous parts of the universe while also carving out the vast dark regions between them. The universe is often envisioned as a dynamic and vibrant cosmos filled with stars, spinning galaxies, and nebulae illuminated by star birth. Spiral galaxies, like the Milky Way, contain hundreds of billions of stars, many with planets and moons. While this energetic view is accurate, it represents only one aspect of the cosmic story. Another side exists that is quiet, cold, and profoundly empty. For every bright cluster of stars or galaxies, there are enormous, nearly vacant regions of space. These are the vast dark areas of the cosmos, and among the most extreme is the Boötes Void. The Boötes Void is remarkably empty by cosmic standards, a condition scientists describe as sparse. Even high-quality vacuum chambers on Earth contain millions of atoms per cubic meter. By comparison, the average density of the universe is extremely low at about 1 hydrogen atom per cubic meter. The Boötes Void is a region of space even more desolate than this cosmic average. In the center of this void, the concentration of ordinary matter, such as atoms, stars, and galaxies, can be 10 times lower than the already low universal average, corresponding to far less than 1 atom per cubic meter. What distinguishes this sparseness is the near-complete absence of luminous matter. Galaxies, stars, and glowing gas clouds are exceedingly rare in the Boötes Void, a region of space that would typically contain hundreds or thousands of galaxies may hold only a few within the void. These galaxies exist in near total isolation. An observer inside the Boötes Void would see an eerily dark sky with only a few faint smudges of light from distant galaxies separated by hundreds of millions of light years. There would be an absence of glowing nebulae, stellar nurseries, and galactic collisions. This profound emptiness is a direct consequence of the arrangement of matter in the early universe. Over 13 billion years ago, the young universe had minor variations in matter density. Denser areas attracted more material through gravity, evolving into the filaments and galaxy clusters seen today. Conversely, the less dense regions were stretched as the universe expanded, causing more matter to drift toward denser areas. This process formed the great voids like Boötes. Although they appear empty, voids are not entirely devoid of matter. Dark matter is present, though more thinly distributed than elsewhere. Dark matter is invisible but detectable by its gravitational effects, and it helps shape the universe's structure. Even in these sparse regions, the behavior of dark matter is also influenced by early density differences, meaning voids carry an imprint of the universe's initial conditions. Additionally, dark energy, which causes the accelerated expansion of the universe, is believed to be uniformly distributed throughout space, including within voids. Voids may be ideal locations for studying dark energy because the low matter density minimizes interference with its effects. Thus, the scientific term sparse describes regions where the components of the universe are so rare and scattered that they challenge conventional concepts of place. Voids are the structural hollows that define the cosmic web, and the Boötes Void is a significant example of the forces that have shaped the cosmos. The gravitational environment within a vast empty region, like the Boötes Void, is entirely different from that of crowded areas such as galaxy clusters. A galaxy cluster contains hundreds or thousands of galaxies in close proximity, constantly interacting through gravity. These interactions can involve galaxies passing one another, distorting each other's shapes, or merging. Such powerful gravitational events influence galactic evolution, affecting star formation, galaxy morphology, and the distribution of internal gases. Inside the Boötes Void, however, the gravitational dynamics are substantially different. The few galaxies that exist there are so far apart that they exert negligible gravitational influence on one another, with the nearest major galaxy groups being hundreds of millions of light-years away. The gravitational pull on galaxies within the Boötes Void is exceptionally weak. Consequently, the galaxies and matter inside are primarily influenced by a gentle tug from sparse, dark matter within the void and a minor pull from distant galaxy filaments at its edges. This profound isolation ensures that these galaxies remain undisturbed by external forces. They are free to move with the universe's expansion, dispersing more slowly and peacefully than galaxies in denser regions. Their evolution is calm and quiet, unaffected by the disruptive events of galactic collisions or significant gravitational interference. The void represents a tranquil area in an otherwise active universe. Cosmic voids, such as the Boötes Void, are distinct from the typical empty spaces found between galaxies. While the intergalactic regions within a galaxy cluster or filament are largely empty, they are still relatively close to dense cosmic structures and contain a thin haze of gas, called the intergalactic medium. This gas can be heated by nearby galaxies undergoing active star formation or by their central black holes. In contrast, cosmic voids exhibit a much higher degree of emptiness. They are immense regions situated between entire superclusters of galaxies. These voids contain significantly fewer galaxies, stars, black holes, and powerful energy sources. The intergalactic medium within them is more rarefied and colder because there are virtually no sources to heat it. This scarcity of gravity matter and energy sources is what defines these areas and distinguishes them from the rest of the cosmos. Voids are analogous to vast deserted landscapes in the universe, largely devoid of the standard components of galaxies. The profound emptiness of the Boötes Void and similar regions makes them exceptionally challenging to observe. With very few stars and galaxies present, these areas emit minimal light. Astronomers must utilize the most powerful telescopes available and conduct observations for many hours or days to gather the scarce light that exists. The rarity and faintness of galaxies within voids demand extraordinary effort and patience to study. However, this same emptiness provides significant scientific value. In regions with a near absence of ordinary matter, the influence of dark energy can be understood more effectively. Dark energy is a theoretical force believed to permeate space and accelerate the universe's expansion. In densely populated areas of the cosmos, distinguishing the effects of gravity from those of dark energy is difficult. In the low-gravity environment of a void, however, dark energy can be observed with greater clarity. By analyzing the expansion rate of voids like Boötes and the distribution of matter within them, scientists can gather critical data on the universe's evolution. This research allows them to test various theories about the nature of dark energy and the reasons for the universe's accelerating expansion. Within the Boötes Void, one of the universe's emptiest regions, there exists a small population of isolated galaxies. Although known for its profound darkness and scarcity of luminous matter, this area is not entirely vacant. A few scattered galaxies are located inside this immense cosmic expanse. These are known as void or lonely galaxies because of their extreme isolation from the densely populated regions where most galaxies reside. These galaxies are so distant from any neighbors that they appear to exist alone in space. In most of the universe, galaxies are situated in active environments where they exert gravitational forces on one another, leading to collisions or mergers that alter their forms. The galaxies inside the Boötes Void, however, do not experience such interactions. They remain undisturbed by these common cosmic events, offering scientists a rare chance to study how galaxies develop when free from the gravitational influence of nearby neighbors. Upon its discovery in 1981, the Boötes Void was thought to be nearly devoid of matter, as initial surveys revealed little besides a dark expanse of sky. With advancements in technology and more powerful telescopes, researchers later detected faint light signals from a few distant galaxies within the void. Currently, approximately 60 galaxies have been identified in this region. This figure is remarkably low, given the void's immense volume. For comparison, a region of equivalent size with an average galactic distribution would be expected to contain thousands of galaxies. The identified galaxies are not grouped together, but are widely dispersed, often separated by distances of 10 to 20 million light-years. From a planet within one of these galaxies, the night sky would appear almost entirely dark with the large-scale structures of the cosmic web, visible only as faint, scattered points of light. The galaxies within the Boötes Void are distinct from those in dense galactic environments due to their isolation. A primary difference is their morphology. In crowded clusters, frequent gravitational interactions can strip gas from galaxies, distort their shapes, or induce bursts of star formation. The galaxies in the Boötes Void, however, are seldom disturbed by such encounters, as they are not subject to significant external gravitational forces and rarely collide. Many have retained their primordial shapes. Most are faint spiral or irregular galaxies that appear relatively pristine, resembling earlier forms in the universe's history. Their structure is governed primarily by internal processes rather than external influences. A further significant distinction lies in their star formation processes. The creation of new stars requires abundant cold gas and dust. In dense environments, this material can be removed by hot intergalactic medium or stripped during collisions, ceasing star formation and causing the galaxy to age, characterized by the dim red light of older stars. The isolated galaxies in the Boötes Void do not experience this issue. Lacking nearby galaxies or dense gas to deplete their resources, they retain their star-forming fuel for extended periods. Consequently, these void galaxies exhibit a slower and more consistent rate of star formation. Many appear bluer than galaxies in clusters, which indicates ongoing star birth. This sustained star formation offers scientists a view into how galaxies might evolve naturally over billions of years, free from the disruptions of collisions or tidal forces. Studying these isolated galaxies presents considerable challenges. They are extremely distant from Earth and appear very dim, as they do not form large quantities of bright new stars. Their light, which travels for hundreds of millions of years to reach us, is faint and difficult to detect. Proper observation requires the use of premier telescopes on Earth and in space for extended periods, often hours or days. Access to these instruments is highly competitive, making each observation opportunity valuable. Furthermore, their isolation creates additional difficulties. Astronomers studying galaxies in clusters or filaments can use nearby bright objects to assist with measurements or to observe phenomena such as gravitational lensing. In the Boötes Void, the absence of such neighbors means each galaxy must be studied independently, relying solely on its own faint light. A final challenge is the small number of confirmed galaxies. With only about 60 known, it is uncertain whether this sample is representative of the entire population of void galaxies or merely reflects the limits of current detection capabilities. It is plausible that numerous fainter, smaller galaxies exist within the void but have not yet been discovered. Our current catalogue of galaxies may be biased toward larger and brighter examples, potentially excluding a population of smaller or more enigmatic objects. Within voids, scientists, however, persist in carefully collecting data. They measure the redshifts of these galaxies to determine their distances and precise locations within the Boötes Void. By analyzing their light with spectrographs, Researchers can learn about their composition, the rate of star formation, and the movement of their internal material. Each observation contributes to our growing understanding. Although studying them can be challenging, galaxies existing in isolation, far from the dense regions of the universe, are of immense scientific value. These solitary galaxies, often found within vast cosmic voids, provide rare insights that assist astronomers in addressing fundamental questions about galactic formation, growth, and evolution. These isolated galaxies serve as a cosmic equivalent of a control group. Most galaxies are situated in dense environments, like clusters or filaments, where they constantly interact through gravitational forces, collisions, and mergers. In contrast, solitary galaxies in vast underpopulated regions of space exist with minimal external interference. By comparing these isolated systems to those in crowded environments, scientists can distinguish between changes driven by a galaxy's internal processes and those caused by its surroundings. For instance, if a galaxy in a dense cluster has ceased star formation due to gas loss, while a similar galaxy in a cosmic void retains its gas and continues to form stars, the contrast suggests an environmental cause. A mechanism in the crowded cluster, such as ram pressure stripping, which removes gas from galaxies, is likely responsible. This comparative approach allows astronomers to better understand how a galaxy's evolutionary path is influenced by its location. Over billions of years, such environmental factors can profoundly shape a galaxy's development. Furthermore, because isolated galaxies have experienced minimal interactions or mergers with neighbors, they may have preserved more of their original characteristics from the time of their formation. This makes them valuable as time capsules that hold clues about the early universe. Studying them can reveal the nature of primordial galaxies, particularly those in regions with low matter density. The future of studying these isolated cosmic objects is promising. New generations of space-based and ground-based telescopes are providing unprecedented views of the universe. The James Webb Space Telescope, launched in 2021, is one of the most powerful. Observing in infrared light, its sensitivity allows it to detect extremely faint and distant galaxies that were invisible to previous telescopes, and it has already started to transform our cosmic perspective. In parallel, large new ground-based telescopes, equipped with advanced technologies like adaptive optics and highly sensitive detectors, are being developed. These facilities will enable astronomers to discover a greater number of isolated galaxies, including the smaller and fainter ones that are currently undetected. Studying larger samples will allow scientists to more thoroughly investigate how these galaxies retain gas-formed stars and develop their internal structures. This research will contribute to a more complete understanding of how galaxies evolve in isolation. It is also interesting to consider what the universe would look like from within one of these solitary galaxies. For any potential intelligent life on a planet in such a location, the night sky would be starkly different from ours. From Earth, our sky is filled with stars, planets, and the luminous band of the Milky Way. In contrast, for inhabitants of a galaxy within the Boötes Void, the view would be significantly emptier. The Milky Way would be too distant to be visible. Their night sky would be predominantly black, featuring only a sparse scattering of stars from their own galaxy. Even with powerful telescopes, other galaxies would appear merely as faint, tiny points of light, hundreds of millions of light years away. For such observers, the universe might seem desolate, possibly leading them to conclude that their galaxy was the only one in existence. Their cosmic perspective would be defined by the vast emptiness of their surroundings, unaware of the immense network of billions of other galaxies. For most of human history, Our cosmic understanding was limited. Initially, we observed only individual stars. We later learned that these stars belong to large systems called galaxies. For some time, galaxies were believed to be randomly distributed throughout space. However, as telescopes advanced and scientists developed precise methods for measuring cosmic distances, our view of the universe changed fundamentally. Researchers discovered not a random arrangement of galaxies, but a vast, organized, and interconnected structure that extends throughout the cosmos. This large-scale structure composed of galaxies, dark matter, and other cosmic constituents is known as the cosmic web. The cosmic web can be visualized as an immense, three-dimensional structure. Galaxies are not distributed uniformly. Instead, they are concentrated along long, thin strands, or filaments. At the intersections of these filaments, galaxies form large clusters known as nodes. The vast, underdense regions between these filaments are the cosmic voids. This entire structure is too large to be captured in a single image. Scientists have constructed this model by mapping the three-dimensional positions of millions of galaxies. By connecting these points, the web-like pattern of galactic distribution becomes apparent, representing one of the most significant discoveries in modern astronomy. The cosmic web consists of three main components that influence the evolution of the universe. The first are the filaments, which are long, thread-like structures, extending for hundreds of millions of light-years. Galaxies are arranged along these filaments, including our own Milky Way, which resides within one in a relatively sparse section of the web. These filaments function as conduits, guiding matter and galaxies toward denser areas, shaped by gravity over cosmic timescales. They are not straight, but rather twist, bend, and branch. Along these structures, galaxies form smaller groups and clusters that are in constant motion, drawn toward larger gravitational centers. The filaments constitute the underlying framework of the universe, influencing the formation, evolution, and motion of galaxies. Their discovery revealed that the universe is highly structured, providing insight into the distribution of galaxies. The second major component of the cosmic web is the clusters or nodes, which are located at the intersections of filaments. These are the most dense and active regions in the universe, containing hundreds or even thousands of galaxies, vast clouds of hot X-ray, emitting gas, and large quantities of dark matter. As the largest gravitationally bound structures, known clusters are held together by their immense gravity. Our own local group of galaxies is part of a larger structure, the Laniakea supercluster within clusters. The proximity of galaxies leads to frequent interactions such as collisions, gas stripping, and mergers which accelerate galactic evolution. The powerful gravitational pull of a cluster continuously draws in more galaxies from the surrounding filaments, making these regions the most dynamic parts of the cosmic web, and a direct contrast to the stillness of the most mysterious and empty regions of the cosmic web. Cosmic voids are the vast, nearly empty spaces located between the filaments and clusters of the large-scale universe. Within these regions, galaxies are exceptionally sparse. The Boötes Void serves as a prominent example, a colossal area of near-nothingness so large that light requires hundreds of millions of years to traverse it. The density of galaxies in such voids can be less than 1/10 of that found in average sections of the universe. While not entirely empty, as they may contain stray atoms or an occasional isolated galaxy, these voids are spatial deserts compared to the dense filaments and clusters. Over time, these voids are expanding. As the universe grows and gravity draws matter toward denser parts of the cosmic web, the voids stretch and become even more vacant. Galaxies that might have once resided within them have been pulled away, creating immense regions of cosmic silence. A single galaxy inside a void can exist in complete isolation, lacking neighboring galaxies or clusters. These solitary environments help scientists understand the uneven distribution of matter across the cosmos and explain why some galaxies are shaped by gravitational interactions, while others evolve undisturbed for billions of years. The filaments, clusters, and voids collectively constitute the grand structure of the known universe, the cosmic web. This universe-sized network formed over billions of years. Galaxies are not distributed randomly, but are intricately woven into a cosmic tapestry shaped by gravity, dark matter, and time. Understanding how immense empty regions like the Boötes Void fit into this structure is fundamental to cosmology. These voids are not arbitrary patches of emptiness, but are integral components of this larger, carefully structured pattern. The formation of this structure can be compared to stretching a large piece of rubber fabric. Pulling on one area makes it denser, while causing other parts to become thinner and emptier. A similar process occurred in the early universe. As gravity pulled matter together to form long thread-like filaments and dense galaxy clusters, other regions were left behind, becoming the spacious and less dense voids. The Boötes Void is a remarkable example of this phenomenon, an enormous region where very little matter collected due to the universe's initial conditions, combined with the effects of gravity and cosmic expansion. This void can be pictured as a giant bubble within a sponge-like structure. It is surrounded by walls, not of solid matter, but of zones where galaxies are concentrated in filaments which form the skeleton of the cosmic web and mark the void's boundaries. The Boötes Void is therefore not separate from the universe's structure, but a crucial part of it, demonstrating how matter is unevenly distributed on the largest scales. The dense parts of the cosmic foam are the filaments and clusters, while the voids are the empty pockets. Our own galaxy, the Milky Way, resides within a small collection of galaxies called the Local Group, which is part of the much larger Laniakea supercluster. We are located in a relatively crowded filament of the cosmic web, not in a void, and are slowly being pulled toward a denser region within our supercluster. The Boötes Void is situated far from our galactic neighborhood, more than 300 million light-years away, in a distinct part of the cosmic map. This contrast between dense galactic highways and silent cosmic wastelands illustrates the immense variety and scale of the universe. The existence of this cosmic web is not merely a theoretical model. It has been confirmed through astronomical observation using powerful telescopes and extensive surveys that measure redshift. Astronomers have mapped the three-dimensional positions of millions of galaxies. Redshift reveals a galaxy's distance based on how its light stretches as it travels through the expanding universe. By combining these measurements, scientists have constructed detailed 3D maps that clearly show the cosmic web. In these maps, filaments appear as long chains of galaxies. Clusters are visible where these chains intersect, and vast dark voids emerge as regions with an almost complete absence of galaxies. The Boötes Void was one of the first and most striking voids discovered, and its immense size and emptiness provided key evidence that the universe is arranged in a complex web-like pattern rather than being uniformly filled with matter. It demonstrated how voids, filaments, and clusters fit together to form a vast cosmic design. Today, increasingly advanced telescopes and surveys are producing sharper, deeper maps that reveal the cosmic web in greater detail, continuing to confirm that voids are fundamental and non-accidental components of the universe's architecture. The universe today contains a remarkable variety of structures, from atoms to massive galaxy clusters spanning millions of light years. However, the universe was not always this way. Immediately following the Big Bang, over 13 billion years ago, the universe was incredibly hot, dense, and almost perfectly smooth. It was a uniform mixture of matter and energy, without stars, galaxies, clusters, or voids. How this smooth, primordial state evolved into the current, lumpy web-like structure is a central question in modern cosmology. The answer begins with infinitesimal differences that existed at the very beginning, which were amplified over billions of years by gravity and cosmic expansion. This process began when the universe was less than a fraction of a second old. Although the early universe was almost completely uniform, quantum mechanics dictates that there were minuscule fluctuations in the distribution of matter and energy. These slight variations in density and temperature are thought to have originated from quantum events that occurred when the universe was smaller than an atom. An event known as cosmic inflation then caused a sudden dramatic expansion that stretched these microscopic ripples across the universe, turning them into the seeds from which all cosmic structures would eventually grow. Some regions had slightly more matter than average, while others had slightly less. From these nearly imperceptible differences, the structure of the cosmos began to form, shaped by the force of gravity. Even though the initial density differences were extremely small, gravity began to act on them immediately. In areas with slightly more matter, the gravitational pull was stronger, which in turn attracted more matter from nearby regions, causing these denser spots to grow larger and more crowded over time. Regions with slightly less matter exerted a weaker gravitational pull. As surrounding matter was drawn toward denser areas, these sparse regions became progressively emptier. This process, where matter is unevenly aggregated, amplified initial density differences. Gravity caused matter to be drawn away from underdense areas and to accumulate in regions that were already dense. Over billions of years, this process intensified the density of dense regions and the emptiness of sparse ones, leading to the formation of both galaxy clusters and vast voids. This phenomenon is known as gravitational instability, a fundamental concept in the growth of cosmic structures. The small initial fluctuations in the universe's density were magnified by gravity over time. Regions with greater matter density began to collapse inward, attracting gas and the substance known as dark matter. These became the filaments and clusters of the cosmic web that are observed throughout the universe today. Simultaneously, the less dense areas expanded more rapidly than the rest of the universe. As gravity drew material away from these regions and toward the accumulating dense areas, they were progressively evacuated of their contents. These depleted regions evolved into the cosmic voids, which are integral parts of the universe's large-scale organization. The entire structure of the universe resulted from gravity sorting matter into dense and empty zones. Another significant component in this process is dark matter, which cannot be observed directly. Unlike ordinary matter, dark matter does not emit, reflect, or absorb light, and does not interact with electromagnetic forces, making it undetectable by telescopes. Its presence is known through its gravitational effects on the motion of galaxies and the structure of space. Scientists estimate that dark matter constitutes about 85% of all matter in the universe, meaning it is more than 5 times as abundant as ordinary matter. In the early universe, slightly denser concentrations of dark matter began to coalesce first. Their gravitational influence attracted more dark matter and subsequently drew in ordinary matter. These initial clumps provided the gravitational framework upon which galaxies and clusters later formed and grew. Dark matter also shaped the voids. Regions with lower initial concentrations of dark matter became these empty spaces. Although voids contain some dark matter, their density is much lower than that of filaments and clusters. The distribution of dark matter was a primary factor in determining the locations of both galaxies and voids. The Boötes Void and similar structures are a natural consequence of billions of years of these subtle initial differences being amplified by gravity, guided by dark matter, and shaped by the expansion of space. From the universe's initial density, ripples all cosmic structures were formed: galaxies, clusters, and the voids between them. In addition to gravity, the continuous expansion of the cosmos is another powerful force shaping the universe's empty spaces. Since the Big Bang over 13 billion years ago, space has been expanding in all directions, causing the distances between galaxies to increase. This cosmic expansion has different effects depending on the scale. At smaller scales within galaxies and galaxy clusters, gravity is strong enough to bind matter together, despite the expansion. At much larger scales between galaxy clusters, the expansion of space is the dominant force. The regions that were initially slightly less dense, which would become cosmic voids, expanded faster than denser regions. The sparse matter within them was pulled progressively farther apart, making these areas even emptier over time. This thinning of matter, due to the universe's expansion, is known as cosmic dilution. Within voids, the stretching of space continually increases the distance between the few particles present, causing the voids to become larger and more empty over time. These voids are a natural result of the behavior of space itself. Their formation, along with the surrounding filaments and clusters, creates the large-scale structure known as the cosmic web. This structure formed over billions of years. To understand this formation process, scientists utilize advanced computer simulations that model a digital version of the universe. These simulations begin with the conditions thought to exist shortly after the Big Bang, including small density fluctuations, a specific mix of ordinary and dark matter, and cosmic expansion. As the simulation evolves over billions of years, it shows the interaction of gravity and expansion on these initial conditions. The structures that emerge in these simulations, including filaments, clusters, and voids, bear a strong resemblance to the large-scale structures observed by astronomers. The Boötes Void is an example of a structure that forms naturally in these simulations, which incorporate the effects of dark matter and dark energy. These simulations also allow scientists to test their theories by altering parameters such as the amount of dark matter or the rate of expansion to see how the resulting cosmic structure changes. This helps researchers understand the fundamental principles that have governed the universe's evolution. However, computer models require validation through astronomical observation. Data from real cosmic voids, such as the Boötes Void, is essential for this purpose. Astronomers measure the positions and distances of galaxies, including the few found within these voids, to test the accuracy of the simulations. The agreement between observations and models provides strong confidence in the current understanding of cosmic structure. The size and emptiness of the Boötes Void are consistent with predictions from models where gravity and cosmic expansion have acted on small early universe density fluctuations over billions of years. The visible components of the universe, such as stars, galaxies, and gas clouds, are composed of what is known as ordinary matter. This matter consists of atoms like hydrogen, helium, and heavier elements. It is the same type of matter that constitutes planets, life, and the air. It is the only kind of matter that can be directly detected by telescopes, because it interacts with light. Modern cosmology, the study of the universe as a whole, reveals that visible matter such as stars and galaxies represents a minor fraction of the total matter in the universe. The majority of cosmic matter is an invisible and influential substance known as dark matter, which is critical in shaping the universe. Dark matter is undetectable by direct observation because it does not emit, reflect, or interact with light. Its existence is inferred from its gravitational effects on visible matter. Evidence for dark matter includes the observation that galaxies rotate faster than their visible matter would allow, suggesting an unseen mass provides the necessary additional gravity. Another piece of evidence is gravitational lensing, where light from distant galaxies bends around invisible mass, indicating the presence of more matter than is visible. The formation of the universe's large-scale cosmic web, a structure of filaments, clusters, and voids, is also attributed to the presence of dark matter. It is estimated that dark matter constitutes approximately 85% of all matter in the universe, making it the primary agent in sculpting its large-scale structure. The origin of this cosmic structure dates to the period shortly after the Big Bang, approximately 13.8 billion years ago. The early universe, while hot, dense, and largely uniform, had minor density variations, thought to originate from quantum fluctuations. These primordial fluctuations existed in both ordinary and dark matter. Since dark matter was the dominant component, its gravitational influence was greater. Regions with slightly higher dark matter density began to attract more matter, serving as the seeds for the formation of all modern cosmic structures. Through a process known as gravitational instability, gravity acted over billions of years on these initial seeds. Denser regions gradually drew in more material, causing small concentrations of dark matter to grow into larger structures, eventually forming invisible dark matter halos. These halos acted as gravitational wells, attracting ordinary matter like gas and dust, which then cooled and condensed to form the first stars and galaxies. Present-day galaxies remain situated within these massive dark matter halos. Dark matter provides the underlying framework for the universe, giving structure to galaxies and drawing them into larger formations. In its absence, the gravity of ordinary matter alone would have been insufficient to counteract cosmic expansion, preventing the formation of stars and galaxies. In addition to facilitating galaxy formation, dark matter was instrumental in creating the universe's large voids, such as the Boötes Void. Regions with initially lower densities of dark matter had weaker gravitational fields. Consequently, as matter was gravitationally attracted to denser areas, it was simultaneously drained from these underdense regions. This flow of matter shaped the cosmic web, creating vast voids between galactic structures. The Boötes Void likely originated as a region with a dark matter concentration far below average, which over cosmic timescales became largely empty as gravity drew matter toward denser surroundings. Although invisible, dark matter is fundamental to the cosmos. It served as the architect that constructed galaxies, formed filaments, and created voids. Dark matter is present even in the most empty regions, such as the Boötes Void, though in significantly lower concentrations. In contrast to galaxy clusters and filaments, where dark matter is densely concentrated, the dark matter within a void is sparse and diffuse, resulting in a much weaker gravitational influence. This affects the few galaxies residing within voids, which evolve in relative isolation. These galaxies are nevertheless held together by their own smaller dark matter halos. The presence of dark matter, even in these rarefied regions, demonstrates its pervasive influence throughout the cosmos. The significance of dark matter is also evident in the large-scale structure of the universe. The cosmic web is built upon an underlying framework of dark matter, and the visible galaxies are merely the most luminous components of these much larger invisible structures. Computer simulations of cosmic evolution since the Big Bang successfully replicate the observed structure of the universe only when they include dark matter. Models based solely on ordinary matter fail to produce the complex web of filaments, clusters, and voids. The consistency between these simulations and astronomical observations provides compelling evidence for the existence of dark matter, indicating it is an essential component of the universe's structure and history. The Boötes Void exemplifies the dual role of dark matter. It aggregates matter to form structures while also evacuating matter from other regions to create vast empty spaces. The study of large cosmic voids provides astronomers with insights into how dark matter shaped the overall design of the universe, creating both concentrations of luminous matter and expansive regions of emptiness. While dark matter gravitationally attracts matter to shape cosmic structure, another unidentified force acts in opposition to it. A strange energy known as dark energy exerts a repulsive force that stretches space itself, whereas dark matter acts as a cosmic adhesive pulling material together. Dark energy functions like a cosmic wind, pushing everything farther apart. Its effects are particularly evident in the universe's vast, empty cosmic voids, such as the Boötes Void. Although dark energy is invisible, its presence is felt throughout the cosmos, filling every region of space, even those nearly devoid of matter. It is the primary driver of the universe's expansion. While dark matter's gravitational influence helps form galaxies and galaxy clusters by pulling matter together, dark energy stretches the fabric of the universe, causing the space between galaxies and within empty regions to expand at an accelerating rate over time. This mysterious force was discovered only a few decades ago, fundamentally altering scientific understanding of the universe. Prior to its discovery, astronomers believed the universe's expansion, which began with the Big Bang approximately 13.8 billion years ago, was slowing down due to the collective gravitational pull of all matter, much like a thrown ball slows and falls back to Earth. In the late 1990s, two independent teams of astronomers made an astonishing discovery while studying distant supernovae, which are powerful stellar explosions. These events serve as standard candles, objects of well-understood intrinsic brightness, allowing their distance to be calculated by comparing their known luminosity to their apparent brightness from Earth. The astronomers also measured the light's redshift from these supernovae to determine how fast their host galaxies are moving away. The teams expected to find evidence of a decelerating cosmic expansion. Instead, they observed that the distant supernova were dimmer and therefore farther away than predicted. This surprising result indicated that the universe's expansion is not slowing down, but is instead accelerating. The discovery led to the revolutionary concept of an invisible force, now called dark energy, that is pushing the universe apart at an ever-increasing rate. Unlike dark matter, which clumps together to form galaxies, clusters, and the cosmic web, dark energy is distributed smoothly and uniformly throughout the universe. Its density is roughly the same, everywhere from within dense galaxy clusters to the most remote voids. It acts as a form of anti-gravity, pushing matter apart rather than pulling it together. As the universe expands, the influence of dark energy becomes stronger relative to gravity, which weakens over large distances, Consequently, dark energy's role in shaping the cosmos becomes more dominant over time. This phenomenon significantly impacts the evolution of the universe's large-scale structure, especially within cosmic voids. In dense regions like galaxy clusters and filaments, gravity is strong enough to overcome dark energy's repulsive force, allowing these structures to remain gravitationally bound and even grow through mergers and accretion. In these areas, dark energy's effects are present but are overpowered by gravity. In contrast, voids are immense regions with very little ordinary or dark matter, resulting in extremely weak gravitational fields. In these low-gravity environments, dark energy dominates. Voids are the locations where dark energy's effects are most pronounced, causing them to expand even faster than the universe as a whole. As they grow larger and emptier, they serve as ideal natural laboratories for studying dark energy with minimal gravitational interference. By measuring their expansion rates, their evolving shapes, and the behavior of the few galaxies within them, astronomers can test theories about dark energy. If dark energy is a constant, as proposed by Albert Einstein's cosmological constant, voids should expand in a predictable manner. If it varies in time or space, the expansion patterns would differ. Studying the growth of voids thus allows scientists to investigate the true nature of dark energy and its influence on the ultimate fate of the universe. The Boötes Void, one of the largest such structures discovered, is particularly important. Its vast empty nature offers a unique opportunity to observe the effects of dark energy as it stretches and reshapes the cosmos. The accelerating expansion driven by dark energy will determine the universe's long-term future. As dark energy's dominance over gravity increases, gravitationally unbound structures such as separate galaxy clusters will drift apart at increasing speeds. Eventually, they will cross an observable horizon, a point beyond which their light can no longer reach us, causing them to effectively vanish. The cosmic web, the vast network of galactic filaments and clusters, will stretch and become more fragile until its connections break, causing the structure to unravel. Voids will grow more desolate. Over billions of years, each galaxy or gravitationally bound group will become an isolated island in an immense dark void. Communication or observation between these islands will cease, as the light from distant galaxies becomes so stretched by the expansion of space that its wavelength is rendered undetectable. In this distant future, galaxies will age, stars will die, and the surrounding voids will grow larger and quieter, becoming symbols of an accelerating universe composed of vast oceans of emptiness, separating the last remnants of galactic light. Measuring an enormous empty region, like the Boötes Void, is a unique challenge, as it is defined by the absence of a large number of galaxies. The process is indirect, relying on advanced telescopes and a precise understanding of how light travels through space. Astronomers do not observe the void itself, but to comprehend the structure of the universe, a three-dimensional map is required, which necessitates knowing the distance to each galaxy, not just its position in the sky. This mapping process begins with powerful ground-based and space-based telescopes. Ground-based observatories, such as the European Southern Observatory's Very Large Telescope in Chile and the Keck Observatory in Hawaii, are situated in locations with clear, dark skies and use mirrors several meters wide to collect as much light as possible. Space telescopes like the Hubble and James Webb. Space telescopes operate above Earth's atmosphere, avoiding atmospheric distortion to capture ancient light from distant galaxies. Once a telescope collects light from a galaxy, the light is directed through a spectrograph. This instrument functions by splitting the light into its component colors, producing a spectrum that displays a pattern of dark and bright lines. These lines serve as unique identifiers for the chemical elements such as hydrogen and helium present in the galaxy, as each element produces a distinct and consistent pattern. Astronomers analyze a galaxy's spectrum to identify these familiar elemental patterns. The position of these spectral lines is critical for determining distance. The expansion of the universe causes nearly all distant galaxies to move away from us. As a source of light recedes, its light waves are stretched, shifting them toward the red end of the spectrum in a phenomenon called redshift. The greater the redshift, the faster the galaxy is moving away. According to Hubble's law, a galaxy's recessional speed is proportional to its distance. By measuring the extent of the redshift in a galaxy's spectrum, astronomers can calculate its distance. Measuring the redshifts of many thousands or millions of galaxies allows for the construction of a large-scale three-dimensional map of the universe, revealing clusters, filaments, and vast empty regions like the Boötes Void. To define the size and shape of the Boötes Void, astronomers must collect a vast amount of redshift data from millions of galaxies across large sections of the sky. This is a long-term effort undertaken by large scientific projects like the Sloan Digital Sky Survey, SDSS, and the 2-Degree Field Galaxy Redshift Survey, 2DFGRS. These surveys systematically scan the sky over many years using specialized instruments to simultaneously capture the spectra of thousands of galaxies. From each spectrum, scientists determine the galaxy's two-dimensional location on the sky and its distance, which is calculated from its redshift. Combining the position and redshift data for millions of galaxies creates a three-dimensional map of the universe. This map reveals a grand structure of long thread-like filaments where galaxies are concentrated, as well as dense clusters where filaments intersect. The map also shows vast regions where galaxies are absent, which are known as voids. The Boötes Void is one of the largest and emptiest such regions ever discovered. Voids do not have sharp, clear boundaries. Instead, they are identified using computational methods that detect areas in galaxy maps, where the galaxy count drops significantly below the average. The emptiness of a void is quantified by its density contrast, which compares its galaxy density to the average density of the universe. The Boötes Void has an extremely high density contrast, making it one of the most underpopulated regions known. To understand the size and shape of voids, astronomers use a technique called percolation analysis, which helps reveal how large empty spaces in the universe are connected. The boundaries of voids are not sharp, but gradually transition into surrounding filaments and clusters. Consequently, the Boötes Void is not a perfect sphere, but rather a large bubble-like region shaped by the gravity of the dense cosmic structures surrounding it. Matter appears to have been pulled away from this central region, clumping together to form the walls of the cosmic web. A key aspect of studying the Boötes Void involves observing the rare galaxies that exist within it. The presence of these lonely galaxies confirms that the void is incredibly sparse but not completely empty. These galaxies are difficult to observe because they are very distant and often faint due to low rates of star formation. Powerful telescopes and long observation periods are required to collect sufficient light to study them. By measuring their redshifts, astronomers can confirm that these galaxies are truly located within the void. Studying their characteristics, such as shape and gas content, provides insight into how galaxies evolve in isolated, gravitationally quiet environments away from the interactions common in crowded cosmic neighborhoods. Future studies of cosmic voids will utilize new technologies to map the universe with greater clarity. Upcoming galaxy surveys will be capable of observing fainter and more distant galaxies over wider areas of the sky, which will help refine three-dimensional cosmic maps. Some of these new instruments will observe in the infrared spectrum, which is important for detecting galaxies obscured by cosmic dust. These advanced tools may also reveal more isolated galaxies located inside the Boötes Void, rather map its structure by collecting data from the few galaxies located within it and those that trace its boundaries. By piecing together information from faint light that has traveled for millions or billions of years, scientists can construct a map of this cosmic emptiness. This work is an example of scientific ingenuity, demonstrating how the faintest signals of light can be used to picture the universe's grand structure. The primary method for measuring and mapping these cosmic gaps is the Galaxy Redshift Survey. We'll end it off right there. Thank you guys so much for watching this documentary. Be sure to like this video and subscribe.